First, thank you very much for this very good, interesting conference, and I'm very glad to be present. And so the title of my talk is about the Broglie double solution, and this is a joint work with my PhD student Pierre Jamet. And just to say that we have a preprint for this work on arXiv currently. So in order to introduce you the idea of this work, it's good to go directly to the Broglie PhD thesis in 1923, when he developed what he called his grand idea, it's a grand idée, which was to associate to every particle, like an electron at that time, a particle of mass m in a rest frame, so the rest energy, to a frequency of internal clock, okay, so harmonic internal clock. And then it was inspired, of course, by Einstein relation for the photon. And this has been already discussed in some talk a few days ago. But of course, it doesn't work really, because it realized immediately that if you go to the laboratory frame where the clock and the particle is moving with a certain velocity, you have a Lorentz transformation, so you have a Lorentz contraction for the frequency and the dilatation for the energy. So you don't maintain the connection between frequency and energy. And he found the solution, which is to add another parameter, so to add the wave, which is always in synchronization, synchronized with the clock. So it means that the frequency of the clock and the wave are in the rest frame identical. And this is nice because now when you go to the laboratory frame, what you got is a phase wave, which is completely, which is propagating and which is associated with a faster than light velocity. And what is also very great is that you can recover now the formula for the energy and the momentum if you identify the energy with the frequency of the wave and the wave vector with the momentum. And also you can, if you go to if you identify the position and the wave to the position of the particle, then you can also justify the formula for the frequency of the clock. So this is very nice, and this is one of the most known relativistic reasoning. Even sometimes it's plain textbook of quantum mechanics, and sometimes it is we have the feeling that the Broglie stopped here and then it go to retirement. But of course, this is not true at all, because it was in 1923 and he died in 1987. So what he did, in fact, one thing that he did is to try to find an equation, fundamental equation for this U field, this wave that he called U, and this is what he called double solution, for reason which will become clear later. So it started with the simplest wave equation you can imagine, the D'Alembert equation. It was in 1925, and then he jumped quite quickly to the Klein-Gordon equation that he invented, by the way, together with Schrödinger, and before Klein and before Gordon. And then 25 years later, he came back to this kind of theory after the work of David Bohm, and then decided to use nonlinear wave equation. So the idea of his program, of his research program, was to identify a particle to a kind of soliton, which is propagating on a base wave, okay? And yes, this is a very nice project, but today I'm going to show you a model a bit simpler, which is more in harmony with the initial work of the Broglie. So you have a free system, you have a particle, which is a point-like system, you have internal clock, and you have a wave. And just to say that this is based on some previous work, one by Yves Couder, that independently of the study of the bubble, of the droplet, excuse me, he was watching something about self-adaptive oscillator, and it was at the end of the 90s. And then there's a very nice paper by Christian Borghesi. The name was mentioned several times in previous talks. So it was a relativistic model, and many things, many common points with this model are present in our work. Some difference as well, but I will not detail this today. And last year we published a paper. It was a non-relativistic model, which was also based on the same kind of analogy. And today it will be a completely relativistic approach in presence of external field, external electromagnetic field. So it's it's a bit to see where we can go with this kind of approach. So since it's completely relativistic and covariant model, it's good to start with the action principle or the Lagrangian if you prefer. So you have different elements in this model. So first you have a particle. So the particle is defined by a great simple action principle. We have the proper time here in a relativistic model, and you have the mass. But the mass here is not constant mass. It's a mass associated with also internal oscillator. So it's reminiscent of the internal oscillator of the Broglie. And this is already a nice system because you have already 2 degrees of freedom. But you can add more. First, you need to have add holonomic constraint, which is fundamental in our model. So it means that you have here a Lagrange multiplier, and you have this difference between Z and U. And when you make the variational principle with respect to this Lagrange multiplier, which is also kind of internal force, you obtain Z equal U, meaning that you have a kind of synchronization or phase harmony between the two, the wave and the clock. So I will come back to that. And there's also 2 parts in the action which are quite easy to understand. This one is an interaction between the particle, the center of mass, and the electromagnetic field, so external electromagnetic field. And here there is a term, a Lagrangian term for the field. So it's a kind of D'Alembert-Klein-Gordon equation, something in between. And I will come to that after, a bit later. So the model can be, you can write the earlier Lagrange equation for this model, but they are quite complicated. Fortunately, there is one regime which is very simple, which is very nice, which is the so-called transparency regime, also called symbiosis by Broglie. And this happens when the so-called Lagrange multiplier vanishing. So it means that somehow that the 2 systems, wave and particle, are ignoring some orbit, but they are still connected through the holonomic constraint, which is always valid. So this is the holonomic constraint. And then you get a set of coupled equations. So this one is quite simple. It says that the internal oscillator is simply free harmonic oscillator. So you can solve it. Remember that this is the proper time. This is not the laboratory time. And also for you have the center of mass is following simply the Lorentz force equations. It's quite easy to understand. You have an acceleration, you have the electromagnetic field, and they have a velocity. And here you have effective mass, which is constant in this case. And finally, you have a wave equation, which is looking like that, which is a bit like the D'Alembert equation or the Klein-Gordon equation, if you want, but there's no mass term. It's important to observe in this equation. So what can we do with this thing? So the first thing to do is to recover the uniform motion that was studied by the Broglie originally. So for this, we remove the external field, and simply we say, okay, we have this set of equations. So these are the same as before, and the acceleration now is vanishing, and the wave equation is simply the D'Alembert equation. This can be easily solved, for example, in 1D. So in 1D, you go to the rest frame. So the rest frame, you have the D'Alembert equation like that, and you try a simply stationary wave equation, which is in 1D simply something like that. And if you use this, and you can consider the other equation, and then you see that you have this phase harmonic condition of the Broglie, which is fitting very well. The particle is at rest. The frequency of the clock equal the frequency of the wave. The amplitude of vibration of the clock equal the vibration of the wave. So this is already something interesting. And now if you go to the laboratory frame, you get something like that. So the wave is a scalar, so it's invariant through the Lorentz oscillation. And you got, if you compare with this one, you got the amplitude time a phase. So the amplitude is a group wave, and which is propagating at the velocity of the particle. And the phase wave here is reminiscent of the phase wave of the Broglie, and it is a solution of the Klein-Gordon equation. So this is the reason why this is called double solution. You see, double solution is called like that because you start from a wave equation for the U field, which is here the D'Alembert equation, and you got at the end a wave equation for the phase term, the phasor, which is Klein-Gordon equation. So this is the double solution because you have 2 waves. And now the thing is that another nice property, which was also explained in the talk of Anya Magliaceto at the beginning of this conference, is that you can consider this system as a sum of 2 counter-propagating waves. So two Doppler shift waves, but they are propagating at the velocity of light. So this is interesting because you can see the structure of the wave can be expanded in different ways. And this is playing a role in the next part of the talk. So now what we do is, I want to show you briefly an animation to see how it works. So this is based on a 1D string analogy for our previous paper. So the blue wave is in the total field is in blue, so you can see it's a complicated pattern. You have the group wave, which is moving very slowly at the velocity of the particle, and you have the phase wave, which is very long wavelength, which is going very fast and faster than the particle, by the way. So this is a good illustration of the dynamic of the Broglie. So okay, let me stop that. And yeah, so now let's go to another system which is more interesting, and this is the atom. So I remind you that Niels Bohr, 1913, developed a model of quantum atoms. So based on the quantization of orbital angular momentum. And Sommerfeld later explained that with the quantization of the Maupertuis action, which is defined here. And de Broglie was fascinated by this relation and immediately realized that this is connected with his own theory, because he says that if you associate the momentum to the wave vector, then you have a vortex somehow, and you have the phase should be univocally defined. So you have to have this quantization of the phase along the orbit, and this is completely equivalent, and so that's it. He says we have the model of the atom, and I think it's nice. But what is not often said that the Broglie only used this phase wave in this analogy, not the total U field that he wanted in this model. I remind you that originally in the model there is a group wave as well. Okay, so this is not exactly what he did. There is a separation between the phase wave and the U wave, and people generally don't consider this. But in our model, we can try to see this more in detail because it's quite complicated. In fact, if you try to see this in our model, now we have again this transparency condition. So this is important, and now the mechanical motion of the particle is simply the Coulomb force. So it's easy to understand that if you have, for example, a circular motion, then you have a formula which is quite easy to obtain in a relativistic domain. You have the mass, the parameter gamma containing the velocity, the radius of the orbit, and then the fine structure constant of Sommerfeld, which is defined here, the square of the charge, which is 1/137 approximately. And this is also completed by the quantization formula, where you say that this action is integral number n here. Actually, here for the moment is not yet an integer. Okay, it's just a number. It's just a convenient notation for having something which is similar to Niels Bohr formula. But you see that if you use this notation, then you cover the Niels Bohr formula in a relativistic domain. So the velocity is like that, is 1/n. The radius is complicated formula, also for the energy. And if you go to the non-relativistic regime, you got back the Balmer, the famous Rydberg-Balmer formula, where you have this 1/n squared here. Now, you need the wave to couple to this model in order to solve the double solution. So what we do is first to watch the problem from a pictorial point of view. You say, okay, imagine you have two counterpropagating waves along the orbit. Okay, and these two waves are associated with some kind of orbital angular momentum, so an m plus and minus, and this has to be quantized because the wave has to be univocally defined. So this is a quantization condition for the waves, and so you have some already nice property for the two wave vector, but you have also some more degree of freedom because this can be justified with the 3D calculation. But actually, the frequency has not to be equal to the wave vector because you are actually moving along the orbit. So this is a nice thing. You can add an increment. So this is playing an important role. And now you use the same trick as before for the uniform motion, and you say, okay, we have two waves, so a plus and minus, and you say, fine, you got it like that. You can sum the two waves, and you got a phase and a group wave. You can define some wave vector and some frequency for the wave. And what is nice is that you get an analogy between the group velocity of the wave and the particle velocity in classical mechanics. And this is working because you assume that wave vector and momentum identical. It's also energy, moment, and wave frequency. And this works if the parameter in your dispersion relation is tuned as you need, exactly as to be equal to the external field. And this is possible to do that. And when you do this, then you can obtain, you have a completely self-consistent model. But it's important to observe that you have a two quantum number, m plus and m minus, and then you can also write them as the difference and the sum. And they have not to be integer, because if m plus and minus are integer, this one can be half integer as well. So a priori in our model, we can show that this quantity here can be also half integer. So we have more than simply the Bohr-Sommerfeld method. It could look like some spin if you want, because at the beginning of quantum mechanics, this was linked with spin, the half quantum number. But here we don't want to have this half quantum number, and in fact, this can be removed. I will explain in the next slide, but just to show also that this condition about the so-called holonomic condition also implied that the wave vector, the frequency, the internal frequency of the system is connected to the other parameters of the motion. So you have here a nice dispersion relation which can be used in our model. Well, so the thing which is interesting that is which is coming directly from the equation is that the quantum number, the small n and the big N, which are defined here, are not independent. They are related to the constant of Sommerfeld by that way, or equivalently in this formula. And this means that actually, if you choose alpha, or more exactly 1 over alpha integer, then you will have a selection rules, and you can eliminate the half integer number, and then you can force somehow the number, the small n to be an integer, and like that you recover the Bohr-Sommerfeld condensation condition. Well, so what you get now, if you solve that, you have to believe me. If you solve the problem in 3D, you got the following things. Then the blue lines here represent the wave along the trajectory for different for the three first trajectory, and the red one represents the phase wave of the Broglie. So you see they are quite different, but anyway, it's a modulation, so this is not a contradiction, and this is fitting well. And if you go to the 3D case, really, if you make the computation, you can see then you can make the map of the wave around the trajectories. This is the plane of the trajectory itself, and this is perpendicular to the plane of the trajectory. So you get donut shape like that, and this you can see the trajectory here. So this is also visible that you can do that to higher order, so n1, n2, n3. This is a larger quantum number. Always you get these kind of things here in the donut shape trajectory. Well, so sorry, I go a bit fast, but now what are the conclusions of this model? Okay, the conclusions are we started with a model with you have particle, you have clock, you have wave, you have different conditions. You use the transparency condition that called like that. With the kind of decoupling between particle and clock, you have this wave equation here, which is very interesting because it's looking like the Klein-Gordon equation, but it's not really the Klein-Gordon equation. There is no mass term here, and importantly, there's this phase harmonic condition here. And then what you get at the end is this thing. You obtain a wave which is a group wave times a kind of phase wave, which is solution of the Klein-Gordon equation. And this is the really the double solution program of the Broglie. In this limit of where we are working, of course, because we are somehow trying to recover Bohmian mechanics. So it's indeed what is happening. We recover Bohmian mechanics in the limit of semi-classical regime, which is associated with the Bohr atom, or it's and so you recover this kind of formula, which is the formula obtained by the Broglie at the beginning of his career, and it is reminiscent of also the Bohmian velocity for the Klein-Gordon field. So finally, it's good to say that this is the full set of equations when you are going beyond the transparency conditions, and when you don't impose an n equals 0, and this n here, then you get this set of equations. So here the wave equation contains a source term, which is interesting because it's a memory term. It's integrated along all the trajectory. And there's also this term, which is internal oscillator, which is forced by this term. So you could also put this inside and you obtain you can somehow eliminate this variable and you obtain a couple set of equations. And here, the last one here is interesting because you see that the force is more complicated, the mass is varying in general. And here you have some gradient force, which is similar, you will say, to the force that you obtain in a hydrodynamic community. We have also gradient force, but this is completely covariant. Okay, it's a different approach. And you have the velocity of which is obtained here, which is the Lorentz force. And so many things could be studied here. We studied already some regime in magnetic field. This will be discussed another time because okay. And then we have quantum transition and many body problems, which are probably very interesting to study in the next future. Finally, just to conclude with a slide with a nice sentence of Broglie coming from his book, one of New Perspective in Physics. It's one of my favorite books. I read this book when I was a student, and it changed my life somehow. And this is the translation of this book in English. So the book says that this is a sentence. History shows clearly that the advance of science have always been frustrated by the tyrannical influence of certain preconceived notions, which were turned into unassailable dogmas. I think this should be remembered and maybe taught to students because it's very important. And finally, okay, thank you for this moment, for this phase harmony, and I'm open for questions. Thank you.